In today's lesson, we are going to be looking at solving linear quadratic systems. So you should have already learned how to solve linear systems back in grade 10, and this is going to be kind of an extension of that where we look at trying to solve a linear quadratic system. So let's just do a little bit of review. Let's solve the following linear system using the method of substitution. Right, a couple things to keep in mind when we talk about solving a linear system. What we're trying to do is we're trying to find the point of intersection. We're trying to see where do the lines cross. Now for substitution, that was one of the two methods you would have learned, substitution or elimination. And we are going to use substitution in this case because that's what is going to apply when we solve a linear quadratic system. But again, solving by substitution, for one variable, you form one equation, or by substituting for one variable from one equation into the other. So it should be from, not for. But basically, again, the idea is you are taking one equation and substituting it into another. Let me just take this entire thing out. From. So we have our so we're doing a linear one as an example because that is what we should be familiar with. So we have our two linear equations here. Right? Y equals 3x plus 7, y equals 2x minus 5. These are two lines. Right? This one is roughly looking something like this, and this one is looking roughly something like that. So we want to see, okay, where do they intersect? We could graph them and we could see, okay, where on the graph do they cross? But again, it's not going to be that easy depending on what the point of intersection is or depending on where it is. So what we do in terms of substituting, we have two equations, right? 1 and 2. In this case, we are going to set them equal to each other because they're both set equal to y. So if I know that y equals 3x plus 7, if they cross at some point, then at that point where they cross, the y values have to be the same and the x values have to be the same. So the y values are going to be the same. So that means I can actually just set these equal to each other. So 3x plus 7 is equal to 2x minus 5. Now what I'm going to do, I only have one variable, so I can rearrange and solve for the one variable. Right, I'm going to move the 2x over. It becomes minus 2x. So I just end up with 1x plus 7 equals negative 5. I'm going to move the plus 5 over, or plus 7 over, so I get 1x equals negative 5 minus 7, or negative 12. Or I get x is equal to negative 12. Now that I have my x value, now I need to find my y value. And to find the y value, all we're going to do is we're going to sub the x value back into either equation 1 or equation 2 and solve for y. So it doesn't matter which one we pick, it's going to give us the same answer either way. So I have y equals, let's do the top one, 3x plus 7. Y equals 3 times negative 12 plus 7. Y equals negative 29. So now I have my two coordinates. So therefore, the point of intersection is negative 12, negative 29. So again, I know they're going to cross at the point negative 12, negative 29. So that is solving this system. So that's the solution to this system, or where they cross. And again, this is something that you would have done in grade 10, one of the methods of doing this. Now for solving a linear quadratic system, because we have a parabola and a line, right? The linear is the line, the quadratic is the parabola. it's going to be a little bit different. It's going to be the same idea or the same overall concept, but it's going to look a little different. So we're going to set the equations equal to each other, similar to what we just did, except it's going to be a line is equal to a parabola. We're going to rearrange to set the equation equal to 0. So we're going to basically move everything over to one side. We're then going to solve for x by factoring or by using the quadratic formula. And when we solve, because we've combined the two equations, it's not going to tell us the roots, but it's going to tell us where the line crosses or where the points of intersection are. And then once we find those x values, we can take them, plug them back into the equation, and solve for y to find the y value of those points. Now, with our linear quadratic system, there are 3 possible scenarios. Similar to when we were looking at a quadratic and we had 3 possible scenarios for the x-intercepts, it's the same kind of idea when we're dealing with a linear quadratic system. Right? We could have 2 intersections. So we see an example, the line comes through, it crosses our parabola twice, 2 intersections. Similar to when we would find 2 roots. So our quadratic formula would give us 2 answers. Now this line, by definition, is called a secant. And a secant is a line that intersects a curve at 2 distinct points. And similar to when we were looking at the quadratic formula for the roots, and we looked at the discriminant to tell us how many roots there are, we could do the same thing. So in this case, the discriminant would have to be greater than 0. If we have one intersection, right, we have, or our line basically is called a tangent. So it touches the curve at one point, and the slope of the curve, or the slope of the line, is the slope of the curve at that single point. And again, when we're looking at the discriminant, once we kind of combine the 2 equations, the discriminant would have to equal 0. And similarly, we could have no intersections, right? So the parabola and the line will not touch. And if that's the case, then the discriminant will be less than 0, so we can't really do the square root of anything. So just no solutions, no intersections. So similar to finding roots, we have those same 3 scenarios, except it's where or how many times our line intersects with the parabola. So let's go through and take a look at an example. So we have our 2 equations. We have our f at x is equal to 1/2 x squared plus 2x minus 8, and we have g at x is equal to 4x minus 10. So we have our linear system and our quadratic, or we have our linear quadratic system. So let's set them equal to each other, right? Because we're saying that these 2 functions are going to equal the same thing. So what we're going to do first is we're going to set f at x equal to g at x. So 4x minus 10 equals 1/2 x squared plus 2x minus 8. So I've set them equal to each other. Now what we're going to do is set equal to 0. So I'm going to move everything over to the other side. So I'm going to bring, oops, font's a little too big. I'm going to bring the 4x and the minus 10 over to the other side. So I'm left with 0 equals 1/2 x squared. The 4x coming over becomes minus 4x, so we get minus 2x. And then the minus 10 becomes plus 10, or we have plus 2. So now I've combined everything. So I've combined my 2 equations. Now in this case, we could see if we could common factor, right? We could common factor out the half in front. It leaves me with x squared minus 4x plus 4. So all I did here was common factor. Oops. Let me go back, common factor, set equal to 0. So I've common factored, and I have 1/2 x squared minus 4x plus 4. Now our goal is, or not our goal, but what we want to do is, this question is asking how many points of intersection are there. Oops. So what I can do is I can actually just use the discriminant, which looks at the a value, the b value, and the c value. Is b squared minus 4ac. That was the discriminant. So in this case, negative 4 squared minus 4 times 1 times 4. This works out to 0. So because it works out to 0, we check the discriminant. So because it works out to 0, therefore there's only one solution. Because when we go back and we think about the quadratic formula, we'd be adding, subtracting. So it would only give us one solution. Now what we're going to do is we're going to solve the linear, or we're going to solve a linear quadratic equation to get the exact values. So if I go back to my my quadratic, or my system, right, the minus x squared minus 4x plus 4. Technically we have the 1/2 out front. It's all equal to 0. I can get rid of this 1/2 realistically by moving it over to the other side. Right, so I get 0 is equal to x squared minus 4x plus 4. Again, realistically, it's not going to do much. It's not really of any use when we're factoring or if we're solving the quadratic or using the quadratic formula. It would be helpful if we wanted this equation in factored form, but we're not looking at converting the forms. So looking at this, I could plug these values into the quadratic formula and find the x-intercepts or the x values of the solution, but it's a lot easier in this case, or a lot quicker. I can solve by factoring. Because looking at it, it's a perfect square. It's a perfect square trinomial. So if you recognize the type of trinomial or the type of quadratic it is, and it is easy to factor, in this case it would be x minus 2 squared, then it could be, it's a lot easier than, or a lot quicker than just using the quadratic formula. Now that I have it in factored form, I can set it equal to 0. X minus 2 equals 0. I would essentially do that twice. Either way, it's going to give me the same answer, and I get x is equal to 2. So that means that the x value of the point of intersection, or where these lines cross, or the linear, or the line and the parabola cross, is 2. What I need to do now, or next, different color, I need to plug x equals 2 back into either equation. Doesn't really matter which equation you use, but linear is usually easier. Right? All we're really doing anyways is just plugging it back in and solving. So the linear one would be easier. This would be the g at x is equal to 4x minus 10. So we're looking for g at 2 is equal to 4 times 2 minus 10. Or g at 2 is equal to 8 minus 10, or negative 2. Or another way is just saying y is equal to negative 2. So with all of this, I can say that therefore, the point of intersection is 2, negative 2. So that means this line and this quadratic, they cross. at one point, they cross at 2, -2. So this line would be a tangent. It could be something like this. Is essentially what we're seeing, or what we might see. Next example, we want to solve the following linear quadratic system. So again, same kind of concept, same idea, right? We're going to take the equation. We're going to take the two equations, set them equal to each other. So 10x minus 1 is equal to 3x squared plus 21x minus 5. I'm going to move everything to one side, right? So I'm going to move the minus 1 over and move the 10x over. So it's set equal to 0. 3x squared minus 10x, so plus 11x, so 21 minus 10 is 11. And then plus 1, we get minus 4. So 3x squared plus 11x minus 4. Now that we've moved everything over, we set it equal to 0. Now our goal is to either factor or use the quadratic formula. Again, quadratic formula will always work. It will always give you the values. Sometimes it might not be as easy though, right? Not in terms of like ease, like you're just plugging values into a formula and calculating. However, it might take longer. So if you're more comfortable using the quadratic formula, you're more than welcome to take the A, the B, and the C value, plug it into your quadratic formula, and get your answer, or your 2 answers, or your 0 answers, depending on whatever the case is. This one though, you can factor. It is a complex trinomial, right? So you are looking for 2 values that multiply to 3 times -4 or -12, and 2 values that add to +11. This one actually works out quite well. We have -12, or sorry, +12 and -1. So once I have those 2 values, 3x squared plus 12x minus 1x minus 4. I'm now going to factor by grouping. So factor the first 2 terms, factor the last 2 terms. 3x, and I get x plus 4. And if I factor out a -1, I also get x plus 4. I can now factor out that bracket. X plus 4 times 3x minus 1. So those are my 2 factors. Now that I have those 2 factors, now I can set each factor equal to 0. X plus 4 equals 0. 3x minus 1 equals 0. And I can go through and solve. I get x equals -4. And I get x is equal to 1/3. So these are my 2 x values, or the 2 solutions, or 2 x values for the solutions to this linear quadratic system. This means that it's going to cross at 2 points. So I have the x values. Now I need to go back and find the y value for each one. So I'm going to use the linear system, or the linear equation, because it is going to be a lot easier. So 10 times -4 minus 1. The y is equal to -40 minus 1, or -41. So that means here, therefore, the point of intersection, or point of intersection number 1, is -4, -41. I have a second point of intersection using the other x value that I got. I'm going to plug it into the same one. So 10 times 1/3 minus 1. So this works out to 10 thirds minus 3 thirds gives me 7 thirds. So here, therefore, the point of intersection number 2, or POI number 2, is 1/3 and 7 thirds, or the point 1/3, or 1/3 and 7/3. So there are my 2 points of intersection. So again, look at my quadratic. It does look like it opens up, so it's probably something like this with 2 intersections. So that is what overall the linear system would look like, or the linear quadratic system. Sorry, got to get that kind of wrapped around, right? We're used to linear systems, but now we're introducing the linear quadratic systems. The last one is, if we know some of the information, can we figure out some missing information, right? So if a line has a slope 4, or a line with a slope, or with slope 4, has one point of intersection with the quadratic function, y equals 1/2 x squared plus 2x minus 8, what is the y-intercept of the line? Write the equation, and then write the equation of the line in slope y-intercept form. Right, so slope y-intercept form is just a fancy way of saying y equals mx plus b. And the key thing in this is that it says it has one point of intersection. And that's going to be very helpful, because if it has one point of intersection, or one solution, if you recall, the discriminant must be 0. So it looks complicated, but we're not really going to be going through and doing anything too complicated. We are still going to start off the same way. However, we have our one equation, right? We have our quadratic, 1/2 x squared plus 2x minus 8. That's our linear quadratic system, or that's our quadratic. Our second one, our line, we don't know the y-intercept, but we do know that it has a slope of 4. So we do know y equals 4x, and there's going to be an unknown y-intercept. We're going to call it k in this case. You could say it's b, but we're going to be referring to another b value, so I don't want to try to get it too confused. So 4x plus k. The first step when we're going through and solving the system is we set it equal to each other. So 4x plus k is equal to 1/2 x squared plus 2x minus 8. I'm now going to move everything over to one side to set it equal to 0. So I have 1/2 x squared plus or minus, the 4x comes over, becomes minus 4x, so I'm at minus 2x. And then the k comes over, and it's minus 8 minus k. And I'm putting the k at the end because the y-intercept is a constant. It's going to end up being paired or simplified with the minus 8 anyways. Now, if we were trying to find the points of intersection, now we would go through, we try to factor, we try to find the x values, but we're not trying to do that. We're trying to find what is the y-intercept, or what is this k value. And this is where that one piece of information that we are given comes into play, the one point of intersection. That means that when I do my discriminant, b squared minus 4ac, that has to equal 0. And if I have values for my a, my b, and my c, then I can plug that in and solve. And then it turns out that I do have that. I have my a value, I have my b value, and I have my c value, which has my unknown in it. So I'm going to take those three values and plug them in to the discriminant. So negative 2 squared minus 4 times 1/2 times negative 8 minus k equals 0. I'm going to go through and solve or simplify. I have 4 minus 2 minus 8 minus k equals 0. I have to distribute first, so 4 plus 16 is 2 times 8. Plus 2k equals 0. I can simplify, so I have 20 plus 2k equals 0. Move the 20 over, I have 2k equals negative 20. And now I'm going to solve for k. Let me just move this up because I got one more step to go. Divide both sides by 2. And I get k is equal to negative 10. So now I know my y-intercept. So therefore, the equation of the line must be y equals 4x minus 10. So that is how we solve linear quadratic systems. Now keep in mind the two examples that we went through, we were able to factor them, right? So if I go back, the two we were able to factor, which is probably quicker than using the quadratic formula. Keep in mind you are able to use the quadratic formula. It will still give you your x values that you need for your points of intersection. So if you come across a linear quadratic system that when you set it equal to each other and then equal to 0, if you don't like what you get, like for example, if you don't like this portion here and you're like, I don't want to factor that, I'm not sure if I can factor that, you can use the quadratic formula. Even though in the examples that we did, we were able to factor it because it was a complex trinomial or a simple trinomial. So just keep that in mind if you come across a situation that you can't factor or you're unsure of what the factors are, use the quadratic formula. It might take you a little longer, more calculations, but it will still give you your two x values like we see here, and then you could plug them in and find your y values for the points of intersection. So again, a little bit of a repeat concept of what you've learned in grade 10, but now we've kind of extended it and kind of made it a little bit more complex, but it's still the same kind of general principles. So hopefully it's not too bad.